Hello everyone, welcome back to online video tutorial on hydrology and irrigation engineering. In this class, we are discussing the computation of mean rainfall or determination of average rainfall. So, why we require the average rainfall? See, the average depth of rainfall is required to do so many hydrological problems. So to solve the hydrological problems, so the average depth of rainfall over a significant area is required. And so some of the procedure must be used to connect a rainfall depth to average areas. So average depth of rainfall is also termed as equivalent uniform depth of rainfall. So another name for average depth of rainfall is equivalent uniform depth of rainfall. And here whatever the rainfall which is measured by the rain gauge, so that is called the point rainfall, because it represents the rainfall pattern over a small area, so which is surrounding the rain gauge station. And also, so as we know, rainfall pattern varies widely. It varies from place to place. And the average depth of rainfall over an area can be obtained only if several rain gauges are evenly distributed over the area. So if the rain gauges are evenly distributed, then only you can calculate the average depth of rainfall. But there is a limitation, so you cannot install more number of rain gauges. So this is again a limitation and a drawback. So that drawback can be overcome by following some of the methods. So to calculate the average depth, that is arithmetic mean method, Thiessen polygon method, and isoheitel method. So these are the methods which are used to calculate the average depth of rainfall. So first method is average depth of rainfall is calculated using the arithmetic mean method, okay, or arithmetic average method. So this is a very simplest method, and it is also called as unweighted mean method. Another name for arithmetic mean method is unweighted mean method. And here the average depth of precipitation over an area is determined by adding the rainfall data of all the available stations, dividing it by number of stations. For example, if you take P1, P2 up to Pn are the precipitation recorded at stations 1, 2 up to N, okay, then where N is the number of station, okay, then the average depth of rainfall is calculated as P1 plus P2 up to Pn divided by N, which is nothing but the number of stations, like how you usually take the average, okay. So the same as, so you're going to calculate the average depth of rainfall, that is, so P is equal to P1 plus P2 up to Pn divided by N, so or 1 by N into summation of I is equal to 1 to N into Pn. So this is the formula to calculate average depth of rainfall using arithmetic average method. And this is not a most commonly used method, so this is a rarely used method. And so this this arithmetic average method you can use only reasonably for a flat areas, and also where the gauges are distributed uniformly over an area, and also individual gauge readings variation from the mean is not too large. When the variation is not too large, only in that case you can use this arithmetic average method. So this, and also here, so what are the limitations or drawbacks of this arithmetic average method? So it won't consider the areal variation, and also so it won't consider the uneven distribution of gauges, and also orographic influences also it won't consider. So but gives a satisfactory result for a hilly terrain. So when the orographic influences is considered, so when it consider orographic influences, then it will give good result in case of hilly areas. And also this method is used to determine the missing rainfall values, okay. And also very rapid, so this is a very fast method, you can like by a manual computation, so very rapid method and excellent adaptability in a computer processing. So you can easily do this method in the using a computer. And the second method is a Thiessen polygon method. So this method, is given by A.M. Thiessen, okay, who have suggested this method in 1911. So that's why the name, the method took the name of Thiessen polygon. And so here, this will consider the irregularities, whatever the limitations were there from the arithmetic mean method. So those limitations, irregularities in gauge location, that is variation in a gauge location, so will be considered here in the Thiessen polygon method by giving the weightage to the rainfall record at each station in proportion to the area. Okay, so we're going to give a weightage for the area also. And also this is a very accurate method for a catchment which is having an area of 500 to 5000 kilometers square. So for this area it will give a more accurate result. And so these areas are determined. So first what we are going to do, we are going to determine the area. Then we are going to multiply that particular area for that particular rain gauge station. And we are going to take the average. So that is how we are going to calculate the depth of rainfall. So these areas, whatever the areas are determined graphically. So first we are going to plot the basin area to some scale. And after that, what we are going to locate the rain gauge station within that area and also the nearby areas. Okay, nearby areas, that is outside the areas. And each of these station positions are joined by a straight line. So I'll show you how this method is calculated. So you can see the figure here. So first what we are going to do, so we're going to draw a area, basin area to some scale. And after that we are going to mark the rain gauge station within this area. Okay, and also outside the area which is near to this basin rain gauges. So we are going to mark the position of rain gauges like this, which within the area and outside the area which is nearer. Okay, and later what we are going to do, we are going to join the stations like this. We are going to join the position of this rain gauge stations. After joining the position of rain gauge stations, what we are going to do, we are going to draw a perpendicular bisector for each rain gauge stations. Like here you can see the perpendicular bisector. So we have drawn like this. So for each line we are going to draw a perpendicular bisectors like this. Okay. So now you can see it is forming a polygon. You can see here. So this is again forming the polygon here. And this particular area is again forming a polygon here. Okay, so and this particular is a one more polygon. So we are going to determine the area of this particular polygon. So we are going to determine the area bounded by each polygons, and that areas we are going to consider. We are going to give a weightage for that area to determine the depth. So let us see the formula. So as I said you, so we are going to locate the rain gauge station. So within the area and also outside the area which is nearer. And after that we are going to draw, join the each station by a straight line, and that will form a triangles, and sometimes it will form a quadrilateral also. And so that if it is a quadrilateral, then we are going to divide that into two triangles. Like so if it forms a quadrilateral like this, we are going to divide it by a diagonal. And while that choosing the diagonal, so you have to choose a shorter diagonal. You will get a two diagonals like this also, like this. So you have to select a shorter diagonal, and after that you're going to draw a perpendicular bisectors like this. Okay, on each side of the triangle. Okay, and also extended up to the boundary of the catchment. So that will form a polygon as you see here. So this is the area. You have a station here, 1, 2, 3. Here also one. Here also one. And after that, so you're going to join like this, so where it will form, triangles, and later what you're going to do is you're going to join like this, which will form a triangles, and later you're going to draw a perpendicular bisectors like this, and which will form a polygons. And later you're going to calculate the area enclosed by the each polygon. Okay, and using that area, so you're going to determine the average depth of rainfall, that is using the formula, that is P is equal to P1 A1 plus P2 A2 plus up to Pn An divided by A1 plus A2 up to An. So where the area, the ratio of AI to A, that is the area of station 1 to the total area, is nothing but the Thiessen weight. So you can rewrite this equation as P is equal to summation of I to M Pi AI divided by A. So where this ratio of AI by A is called the Thiessen weight. So as we are giving a weightage for area, so this method is called weighted mean method. And also once weights are known, so once if you calculate the the area that or weight of weight, so then you can easily determine the P. And here, so this will not consider the orographic influence. So, but compared to the arithmetic method, so this method will give you a good result. And because we are considering the rain gauge station outside the basin area also, so that's why it will give you good result. So this is typical example for a Thiessen polygon, how it looks. And so you have a polygon, say like 1, 2, 3. So represents your stations, and A, B, C, D, like those represents the triangles which for polygons, and the A1 to A6 are the areas of the polygons, and weightage is A1 by A. So these is a typical example for Thiessen polygon method. And the last method is a isoheital method. See, isoheight means, so those are the imaginary lines which join the points of equal rainfall, okay, which is similar to your contours. And compared to those two methods, as I've already mentioned in the very first class, so this will give you the more accurate result. So more accurate method is isoheital method. So here to determine the average depth of rainfall, so what we are going to do, we are going to draw isoheights of different values. Okay, so how we are going to draw the contours, in a similar way, we are going to draw the isoheights, okay, in an area. And the mean of two adjacent isoheight values are assumed to be the rainfall over a given area lying between two isoheights. For example, if you take these are the two isoheights, so we are going to take the average, okay, we are going to take the mean or average of these two isoheights, which will represent the rainfall. So between this area, that is the area lying between two isoheights, is the rainfall of that particular the average isoheight values. The average isoheightal values will be equal to the rainfall of the area submerged between two isoheights. And so what is the procedure to calculate the average depth of rainfall by using this isoheightal method? So initially how we have done, that you are going to draw a basin area, okay, and after that we are going to locate the rain gauge station as we have done it in case of Thiessen polygon method. So similarly we are going to do the we are going to locate the rain gauge station, and after that the rainfall depths recorded by each stations are indicated along with the location. So while indicating the station, you're going to indicate the depth of rainfall of that particular station. So after that, you're going to draw a isoheights on the same base map. Whatever the map you have prepared, on the same map, you're going to draw a isoheight. So first, the points of required isoheight are located by a linear interpolation. So you're going to do linear interpolation. So to mark the points of two adjacent rain gauges. And after that, between the 2 points located, the isoheights are drawn. For example, I'll show you here. So you can see here, so you have an area here which is drawn. So that is the catchment boundary. And after that, you're going to mark the station. You can see here. So the station So you have like A, B, C, D. So those are the rain gauge station. And the 7.0, 7.2, 9.1, those are the rainfall values. Okay. So here what we are going to do is, you're going to do the interpolation. For example, you have A and F. A and F is there. Okay. So between that, you're going to do a interpolation. Okay, and you're going to select the value. So using that interpolation value, you're going to draw a iso height like this. And similarly here, you're going to do the interpolation between A and C, and you're going to select the isoid and you're going to draw like this. So these are the iso heights. So where this sub 8, 6, 4 represents the isoheightal value. So after doing this, what you're going to do, so you are going to take the average between two isoheights. For example, if you take 6 and 8, you're going to take the average of these two isoheights. So, and you're going to multiply the area. Okay, so area under this two isoheights. So that you are going to take it for all the isoheights and divide it by total area, you get the depth of the rainfall value. That is, you can see the formula. So P is equal to, so A into A1 into P1 plus P2 by 2, plus similarly like A2 into P2 plus P3 divided by 2 plus up to Pn AN minus 1 into Pn minus 1 plus Pn by 2 divided by total area, you get the depth of rainfall. So what you're going to do after that? So you're going to locate the isoheight by doing the interpolation. And after that, you're going to calculate the area between those two isoheights, and you're going to multiply each area for the average isoheightal value. And that volume of rainfall between any two successive isoheights, that is nothing but area into average area between those isoheights into average of two isoheightal values. That is nothing but depth into area will, which will give you the volume of a rainfall. So this is a formula to calculate the depth of rainfall using isoheightal method. And as I have already mentioned, this is a this will give you a more accurate result, and this is a superior method compared to other two methods. And here, while constructing a isoheight, we are going to consider the orographic effect also. Okay, so that's why it will give you a good result. And but compared to the arithmetic mean method and isoheightal method, this is a slow method. Okay, and also it will give you the best result. And but adaptability for the computer processing, the adaptability is very poor. So these are the three methods which are used to measure the depth of rainfall, to determine the average depth of rainfall. Thank you all. We'll continue in the next class.